Introduction to operating systems. So the next course that we will tackle is about operating systems. So it's one of the fundamental uh, concepts of computer science. So let's start. Introduction to operating systems. Well, a running program does one very simple thing. It executes instructions, many millions, and these days even billions, of times every second. The processor fetches an instruction from memory, decodes it, i.e., figures out which instruction this is, and executes it. It does the thing that it's supposed to do, like add two numbers together, access memory, check a condition, jump to a function, and so forth. After it's done with this instruction, the processor moves on to the next instruction, and so on and so on until the program finally completes. So first, we allocate first memory, then we copy the program to make it a process into a memory to run it. So once it runs, we can only run that in memory, so we call that a process. In that process, it actually saves some register on the fingertip of the CPU while the CPU runs it. So we will gonna discuss that further later, and more so in the future videos. There is a body of software, in fact, that is responsible for making it easy to run programs, even allowing you to seemingly run many at the same time, allowing programs to share memory, enabling programs to interact with devices, and other fun stuff like that. That body of software is called the operating system, as it is in charge of making sure the system operates correctly and efficiently in an easy to use manner. So this body of software that allows the program to be easy to use is actually the operating system. So that's its one of main goal. Now, the OS takes a physical resource such as the processor, memory, and disk. So that's the usual thing that it communicates to, the disk, memory, and the processor. But it usually talks more directly to processor and memory, not so much to the disk because it has a separate software, as we will discuss in the future videos, and transform it into a more general, powerful, and easy to use virtual form of itself. So the reason why we use operating system to run programs is to make it an easy, powerful, virtual form of itself. Thus, we sometimes refer to the operating system as a virtual machine. So another thing is that since this body of software such as operating system allows you to seemingly run many at the same time, it does this through concurrency, which we discussed in the previous video in Node.js, how programs run concurrently. That's the specific program we create, number in stock, na blogging up. Now, we will gonna discuss how the operating system, such as this Windows, run the different program concurrently, and how it share memory, enabling programs to interact with devices. So the memory, how the memory interact with USB, mouse, keyboard, etc., processor, and other fun stuff like that. So these are operating system. Of course, in order to allow users to tell the OS what to do and thus make use of the features of the virtual machine, such as running a program or allocating a memory or accessing a file. So again, in order to allow users to tell the OS what to do, and thus make the use of the features of the virtual machine that provided by this OS, such as running a program or allocating a memory to that program or accessing a file. The OS also provides some interfaces or APIs that you can call. A typical OS, in fact, exports a few hundred system calls that are available to applications. So it provides this system call that a program could use to call to make access on those hardware such as memory, disk, and processor, and other external devices. Because the OS provides these calls to run programs, access memory and devices, and other related actions, we also sometimes say that OS provide a standard library to applications. As a matter of fact, this is the first term used to describe OS. It's just a standard library that provides calls to run programs, access memory and devices, and other related actions such as network as well, right? So those are the hardware that this OS access. Finally, because virtualization allows many programs to run, thus sharing the CPU and many programs to concurrently access their own instructions and data, thus sharing memory. So instructions and data, you can think of that as algorithm and the data structure, thus sharing memory and many programs to access devices, thus sharing disk and so forth. The OS is sometimes known as a resource manager. It's because it determines how those instructions and data structures access memory, disk, and CPU. So each of the CPU, memory, and disk is a resource of the system that the OS manage. Figure 2.1 is this depicts our first program. It doesn't do much. In fact, all it does is call spin. So here, spin 1, a function that repeatedly checks the time and returns once it has run for a second. So it will repeatedly check the time and then returns that when it has run for a second. Then it prints out the string that the user passed on the command line and repeats forever. So let's say we save this file as cpu.c and decide to compile and run it on a system with a single processor or CPU, as we will sometimes call it. Not interesting of a run. The system begins running the program, which repeatedly checks the time until a second has elapsed. Once a second has passed, the code prints the input string passed in by the user. In this example, the letter A. So here, that CPU/CPU and then the string A. And continues. Note the program will run forever by pressing Ctrl C, which is this, which on Unix based system will terminate the program running in the foreground. Again, not background. Running on the foreground. It means it's the currently running process. We can halt the program. So here's what we will see. So you can see it prints out every second A, which is the string we input. So we halt the program. So the program is just a running process. I'm sorry. That program actually is a process. So because it currently running, while the program is just an instructions and some static data, it doesn't actually call program anymore when it's run in the computer like this, when it's in the memory, right, with the disk, network, etc. So here it's a process. Now let's do the same thing, but this time let's run many different instances of this same program. So here, figure 2.2, we run different oh my god, where is that? Oh, I forgot to copy the figure 2.2. Just a moment. there you go. So let's do the same thing, but this time let's run many different instances of the same program. Figure 2.2 show the result of this slightly more complicated example. It turns out that the operating system, with some help from the hardware, is in charge of this illusion. The illusion that the system has a very large number of virtual CPUs. So even though we only execute it in one CPU, because of the OS coordination with the CPU, it provides an illusion that the system has a very large number of virtual CPUs provided on the screen, turning a single CPU or a small set of them into a seemingly infinite number of CPU, and thus allowing many programs to seemingly run at once is what we call virtualizing the CPU. The focus in the first part of this course. So that's actually what makes this software easy to use. So as a matter of fact, this is one of the innovations that made the current technology possible. A program were able to be combined in one operating system or in one standard application such as Windows, that allows you to combine them, that allows for more complicated and powerful programs. So this what this operating system allows. It provides this virtual it separate provide an illusion that it has a very large number of virtual CPU because it took advantage of the idle time of the CPU, or it maximized the instruction or the power that the CPU or modern CPU can be done on our task, on our office task, or any task that we want to do. So here, CPU A, CPU B, it's the same program, but we run 1, 2, 3, 4 of them. As you can see, it looks like the CPU has multiple CPU, but in actuality, it runs this one at a time. But it's just fast, you know. Of course, to run programs and stop them, and otherwise tell the OS which programs to run, there need to be some interfaces that you can use to communicate your desires to the OS. So to run this and then stop the A and then proceed with the B, and otherwise tell the OS which program to run, there need to be some interfaces that does that. So we'll talk about these APIs throughout this course. Indeed, they are the major way in which most users interact with operating systems. So this is actually also how we create our application, Android or iOS or desktop apps. This is how we communicate to Windows on this operating system. Note how we run 4 processes at the same time by using N symbol. So those N symbol are actually one of the ways we interact with the operating system's APIs. Doing so run a job in the background in the ZSH shell, which means that the user is able to immediately issue their next command. So once we run the end, it actually runs a job in the background in the ZSH shell. So kind of like doing a queue, which means that the user is able to immediately issue their next command, which in this case is another program to run. You might also notice that the ability to run multiple programs at once raises all sort of new questions. For example, if 2 programs want to run at a particular time, which should run? So this question is answered by a policy of the OS. So if you're running multiple programs, so how do you decide which to run first? So those are decided by the policy of the OS. So still the OS, but more specifically the policy of the OS. Policies are used in many different places within an OS to answer these types of questions. And thus, we will study them as we learn about the basic mechanisms that operating system implement, such as the ability to run multiple programs at once. Hence, the role of the OS as a resource manager. So, OS is not just one program that communicate. We call the OS in multiple we can describe OS in multiple ways because it's just complex. It actually has millions of codes, so it does a lot of things, but yeah, more specifically it uses its policy to know which process to run at given any given time. Memory is just an array of bytes. To read memory, one must specify an address to be able to access the data stored there. So as we learned in data structures and algorithm, we just need the address of the memory. In actuality, actually, we can access that in an array in O1 time complexity, and the data stored there. So it's just a simple like that, unlike the OS that does many things, right? So to write or update memory, one must also specify the data to be written to the given address. So to write or update a memory, one must also specify the data to be written to a given address. So as we have noticed in the previous data structures and algorithm, our algorithm won't compile if the data, we don't specify the data that we will write or update on that address that we specified. Memory is accessed all the time when a program is running. So when it is a process, because a program again it's just an instructions and a static data. So when it's already a process, you always need a memory. So you cannot run a program or you cannot run a process without a memory. A program keeps all of its data structures in memory and access them through various instructions. So all the data that the program does, such as this right now, the OneNote, it stores this in memory, and it accesses this structure using its algorithm. So that's actually how it does it, and it communicate to OS and then the CPU, right? So like loads and stores or other explicit instruction that access memory in there work. Don't forget that each instruction of the program in memory is in memory too. So each instruction of the program also is in the memory, not just the data structure. Thus, memory is accessed on each instruction fetch. So each instruction of the algorithm fetch, you access memory. So let's take a look at the program in figure 2.3 that allocates some memory by calling malloc. So the output of this program can be found also here. So here, malloc size, so it allocates first the memory, the A1, and then A2, it prints something. So here's what it prints. So the program does a couple of things. First, it allocates some memory, line A1, malloc. Then it prints out the address of the memory, line A2, and then puts the number 0 into the first slot of the newly allocated memory. So here, P equals to 0, that's the A3. That's how we add 0 on the newly allocated memory. Finally, it loops, delaying for a second and incrementing the value stored at the address held in P. So here, we have P equals to 0 at initially, and we have while loop. We have 1 second and then we spin. So this is how we increment. So we use while loop. With every print statement, it also prints out what is called the process identifier, which is the PID. So every print get PID of the running program. This PID is unique per running process. Again, the first result is not too interesting. The newly allocated memory is address 0x200,000. As the program runs, it slowly updates the value and prints out the result. So it's as it runs, the program slowly updates the value of this P and prints out the result. Here, 1, 2, 3, 4. So you can see it has the same process ID and it prints the PID as the same on the left, and we terminate it using Control C again. Now we again run multiple instances of this same program to see what happens. So see figure 2.4. We see from the example that each running program has allocated memory at the same address 0x 200k, and yet each seems to be updating the value of 0x 200k independently. So we run 2 because of the power of operating system to provide virtualization. We run the process and we stop it, kind of like we put the background in the shell and then put it in the queue and run the other, which seemingly make our CPU more than one. So it is as if each running program has its own private memory. So not just CPU, okay, it's also memory. This is the OS virtualizing CPU and memory. So as you can see, 24113 mem1 and the 24114, that indicates its process. So 24113 address start as 0 2000, and then it run 24114 start as 0, and then 1 1 2 2 until we stop it. And yet each seem to be a waiting value. So it is as if a running program has its own memory instead of sharing the same physical memory with other running programs. Indeed, that is exactly what is happening here, as the OS is virtualizing memory. Each process accesses its own private virtual address space. So each process accesses its own private virtual address space. So this process accesses its private virtual space carved for them by the OS from the CPU, or from the memory rather, sometimes just called as its address space, which the OS somehow maps onto the physical memory of the machine. A memory reference within one running program does not affect the address space of other processes. So a memory reference from this 24114 does not affect the address space of 24113 or the OS itself. As far as the running program is concerned, it has physical memory all to itself. So it carves out the OS carves out a specific part in memory for this process that it's contiguous if it's an array that carves out specifically for this process. So a memory reference within one running program does not affect the others, right? So the reality, however, is that physical memory is a shared resource managed by the operating system. So another thing is that since OS is virtualizing memory and CPU, of course, the physical memory is managed by the OS as well. So there is some API calls that allows you to override it, but it's rare because that's the what makes this easy to use is that it virtualizes all the access to hardware, whether it's network, memory, disk, CPU, and there's one exception only for the file system or disk, but we're gonna talk about that later. So exactly how this accomplished is also the subject of the first part of this course on the topic of virtualization. So for this example to work, you make so as far as the running program is concerned, it has physical memory to itself again. So for this example to work, you need to make sure address space randomize is disabled, because address space randomize could, as it turns out, can be a good defense against certain kinds of security flaws. So read more about it on your own, especially if you want to learn how to break into computer system via stock smashing attacks. So that the I mean, for the OS to successfully do this, it needs to disable the address space randomization, which means that it actually needs to um, be organized. It's not random. It needs to have a list on where it puts or carves out the memory for the program. So we will talk about that on how the different access of a program to different hardware such as disk in user mode and kernel mode also is related to this and how we do this virtualization. So um, another main theme of this course is concurrency. So we use this conceptual term to refer to a host of problems that arise and must be addressed when working on many things at once, like concurrently in the same program. The problems of concurrency arose first within the operating system itself. As you can see in the example above on virtualization, the OS is juggling many things at once, first running on one process, then another, and so forth. As it turns out, doing so leads to some deep, interesting problem. So, concurrency is actually a conceptual term to refer to a host of problems that arise and must be addressed when working on many things at once. As you can see, our memory could only remember up to 7 plus or minus 2. So, these are the one that's gonna deal with it. So, the problem of concurrency arose within the operating system itself. As you can see in the example above on virtualization, the OS is juggling many things at once. First, it activate the first command and then put it in a ZSH shell as a background job, and then execute that, and then execute the other command, etc. So we're gonna know how to deal with concurrent problem as well. Although you might not understand this example fully at the moment, and we'll learn a lot more about this code in the later chapters, in the section of the course on concurrency, the basic idea is simple. The main program creates two threads using pthread create. So it creates, that's another interface command, API command that we're gonna discuss in the future video in details. So to create, you can think of thread as a function running within the same memory space as other function. So you can think of this thread as the function that runs in the same memory in that computer or in that program, with more than one of them active at a time. So more than one of them active at a time. So these are one of the ways we handle concurrency. We may be, we may set up some rules to stop this if it's idle, and then start this in memory. But they are in the same space. In this example, each thread starts running in routine called worker. So this thread starts running in the routine called worker, in which it simply increments a counter in a loop for loop's number of times. Below is a transcript of what happens when we run this program with the input value for the variable loop set to 1000. The value of loops determines how many times each of the two workers will increment the shared counter in a loop. When the program is run with the value of loop set to 1000, what do you expect the final value of counter to be? So prompt gcc, we compile it first, then threads.c wall pthreads. So we compile and then we run specifically the threads. /threads 1000, initial value 0, and then final value 2000. As you probably guessed, when the two threads are finished, the final value of the counter is 2000. So when the two create thread are finished, the final value is 2000 as each thread incremented the counter 1000 times. So that's the work for inside their argument here. Worker. Indeed, when the input value of loops is set to n, we would expect the final output of the program to be 2n. But life is not so simple as it turns out. Let's run the same program with higher values for loops and see what happens. So dash dash threads 100,000. So you can see 143,000 and 100,000 again. 137, right? So as it turns out, the reason for this odd and unusual outcomes relate to how instructions are executed, which is one at a time. So the issue with this is that how the threads were executed, which is we run that one at a time. First, we run 100,000 and then another 100,000. Unfortunately, a key part of the program above, where the shared counter is incremented, takes 3 instructions. One to load the values of the counter from memory into a register. So unfortunately, a key part of the program above, where the shared counter is incremented, takes 3 instructions. One to load the value of the counter from memory into a register. So we move a counter from the memory into a register. One to increment it. So if you do not know the register, it's like the fingertip of a CPU. Later we will discuss this further, but it allows you to go back to where the you left the application. So this is one of the ways we do the concurrency. So instead of the stopping all the progress from the previous application when we move between application, the CPU remember that using this register. So this register is like the fingertip for it to continue. Just like we're gonna expand this later, but another key idea is that imagine you're in a desk where you have this lots of documents, so all of the documents are there, right, complete. This registers like the bookmark, so to be able to go back where you left off while writing. Let's say your boss comes in and then do another process such as changing application. So this actually this application actually does take 3 instructions. So again, these instructions are right the functions in our code, our algorithm, right? So any algorithm, any function is an algorithm. One to load the value of the counter from memory into a register. So we load that into the register. One to increment it, which is the worker, and one to store it back into memory. So to increment that using CPU again, and then to store it back into the memory, and to show, because these 3 instructions do not execute atomically all at once, strange things can happen. So because these are increment, we didn't make it concurrent, make it applied at once, by carving, using operating system to carve those operations and then execute that at once. These strange things can happen. It is the problem of concurrency that we will address in great detail in the second part of this course. Now, the crux of the problem, how to build the concurrent program. So, as you have noticed, these concurrent problems happen in normal applications such as the MERN app. So here we will gonna discuss how operating system solve that, and maybe we can learn from that in our increasingly concurrent or multi-threaded application. So how to build concurrent programs when there are many concurrently executing threads within the same memory space. How can we build a correctly working program? So when there are many threads or functions like one we saw in the code exist in one memory space because it's just in one program. How can we build correctly working program, to execute this? So that's the problem we're gonna solve. What primitives are needed from the OS? What mechanism should be provided by the hardware? So what's needed by the OS? What's needed by the hardware to fix this? How can we use them to solve the problems of concurrency? The third major theme of the course is persistence. The software in the operating system that usually manage the disk is called the file systems. So the software in this operating system, which I told you is different, that usually manage this disk is called the file system. So in all other application, which is memory, disk, CPU, network, these are the exception where it has the separate, it's not a separate, but an software dedicated to it called file system. It is thus responsible for storing any files the user creates in a reliable and efficient manner on the disk in the system. So it's the one responsible for reliable and efficient manner to make the operating system easy to use, or the software easy to use. Unlike the abstraction provided by the OS for the CPU and memory, so an OS, another thing is that could be thought of as an abstraction. So instead of us communicating to the hardware and the memory through its lower level digits, language as assembly or logic gates, we just need to deal with how the OS works. So that's we're gonna discuss the importance of abstractions as well. And also, if you would notice, it's in my blog, the Linux part, where the hardware modules store, there's a directory just for hardware modules, which those hardware modules are tasked to communicate with the hardware, and it abstract those things. OS abstract those things from us. So it's like kind of like that, right? So unlike the abstraction provided by the OS for the CPU and memory, the OS does not create a private virtualized disk for each application. So that's one of the difference, one of our crucial difference. It doesn't provide virtualized disk or private. Rather, it is assumed that oftentimes user will want to share information that is in files. So it is assumed that oftentimes users will want to share information that is in files. For example, so when you're writing a C program, so this is like basic things that made this software easy to use, because we know that files that we saved on the disk, we might use that from other process, such as when writing C program, you might first use an editor like Emacs to create and edit the C file. And to create and edit the C file, Emacs nw main.c. Once done, so this Emacs is this program is just a command line again. It's just a process. Once done, you might use the compiler to turn the source code into an executable. So gcc-0 main.c. So this is what we did earlier, right? gcc-0, we compile it main.c. So we need to access those programs, or processes need to access on file. So another thing is that these programs, it's just a command now, but now it is better because most of this has a GUI or associated with them, an icon, right? We can do that in graphical manner. So when you're finished, you might run the new executable like ./main. Thus, you can see how files are shared across different processes. So those processes are actually different up, but we put that in one command line, which is another characteristic of OS that makes them easy to use, which we're gonna discuss in the future videos. First, Emacs creates a file that serves as input to the compiler. The compiler uses that input file to create a new executable file. In many steps, take a compiler. There's actually many steps, There's, if you want to know the exact details, you can take a compiler course for this. Finally, the new executable is then run, and thus a new program is born. You should be using Emacs. If you're using V, there is probably something wrong with you. If you're using something that is not real code editor, that's even worse. So Emacs is just like code editor that we use to edit, kind of like a Visual Studio Code. Visual Studio Code just have this a lot of features and a GUI. To understand this better, let's look some code. Figure 2.6 presents code to create a file /tmp file that contains the string hello world. Where's that? So let's check that. Here. So it's actually a code to create a file /tmp file. Contains the string hello world, right? To accomplish this task, the program makes 3 calls into the operating system. The first, a call to open, opens the file and creates it. So where's the open here? Here, open, int fd equals to open. The second, write some data to the file. Here, int riser hello world. The third, closed. So it does these 3 programs or compiled in one function. So this should have access in concurrently in this one file. So you cannot like avoid that restrict that to the file system. That what makes the file system different. So simply closes file, thus indicating the program won't be writing any more data to it. These system calls are routed to the part of the operating system called the file system. So these system calls are routed to a different software of the operating system called file system, and it has an exception on security restriction for the programs, which then handles the request and returns some kind of error code to the user depending on the result of the writes, updates, or deletion. So the file system has to do a fair bit of work. First, figuring out where on the disk this new data will reside. So it actually doing a lot when issuing this request or processing this request, and then keeping track of it in various structures the file system maintains. So it also keeps track of it using the various data structure the file system maintains. Doing so requires issuing I/O requests to the underlying storage device to either read existing structures or update them. As anyone who has written a device driver knows, so a device this is where the hardware modules come. Getting a device to do something on your behalf is an intricate and detailed process. It requires a deep knowledge of the low-level device interface and its exact semantics. So it's hard. Operating system abstract it for us. Fortunately, the OS provides a standard and simple way to access device through its system calls. So that system device, such as this OS, provides a simple way to access that. So it's abstracted from the program. In this case, for file system, we use open, write, and close. Thus, the OS is sometimes seen as a standard library, which again, as I've mentioned, the first term used to describe OS. Of course, there are many more details in how devices are accessed, and how the file system manage data persistently atop said devices. For performance reasons, most file systems first delay such writes for a while, hoping to batch them into larger groups. So most file systems, instead of saving immediately the one you save in your Word, it actually waits for a while, hoping to batch them into larger groups, maybe when you before you shut down, etc. To handle the program, or maybe later in the later part of the processing, maybe when there's not much process are running on the foreground. To handle the problems of system crashes during writes, most file systems incorporate some kind of intricate write protocol, such as journaling or copy on write. So in case there's crashes, they use journaling or copy on write algorithm, carefully ordering writes to this to ensure that if a failure occurs during the write sequence, the system can to a reasonable state afterwards. Kind of like the register, how register are used to concurrently run processes. So it also used an algorithm or intricate algorithm for dealing with that. But again, it's abstracted to us by this device on how to communicate on the device in details and the file system in detail. So fortunately, OS provide us system calls to make it easy to access input and output. But as we will later discuss, some processes, or by default, we need to be those I/O limited, especially if we have multiple users running operating systems. So we need to provide those as well. That's where Windows, are able to scale their like work from home setups. They were able to control this operating system with multiple users running multiple operating systems. But that's a topic of a different discussion. So to make different common operations efficient, file systems employ many different data structures and access methods. So it's kind of like in about phase, because this is such fundamental operations in file system. You need to be intricate in employing your software, or designing your software. As you can see, it has a different data structures and access methods to make this normal or useful operations, such as saving, deleting in a file system, more manageable. So from simple list to complex B-trees. So it's use simple list data structure to complex B-trees. If all doesn't make sense yet, good. We'll be talking about all this quite a bit more in the third part of this course on persistence, and where we'll discuss devices and I/O in general, and then disk, reads, and file system in great detail. So the crux of the problem: how to store data persistently. The file system is the part of the OS in charge of managing persistent data. What techniques are needed to do so correctly? What mechanisms and policies are required to do so with higher performance? How is reliability achieved in the face of failures in hardware and software? Another thing is that policies are answer which process run first, while mechanism answers how do you actually process that from OS to device. So we will discuss that further. One of the most basic goals is to build up some abstraction in order to make the system convenient and easy to use. Again, so abstractions are fundamental to everything we do in computer science. Abstraction makes it possible to write a large program by dividing it into small and understandable pieces. To write such program in a high-level language like C without thinking about assembly, to write code in assembly without thinking about logic gates, and to build a processor out of gates without thinking too much about transistors. Abstraction is so fundamental that sometimes we forget its importance, but we won't here. Thus, in each section, we'll discuss some of the major abstractions that have developed over time, giving you a way to think about pieces of OS. One goal in designing and implementing operating system is to provide high performance. Another way to say this is our goal is to minimize the overheads of the OS. These overheads arise in a number of forms: extra time, more instruction, and extra space in memory or on disk. We'll seek solutions that minimize one or the other or both if possible. Perfection, however, is not always attainable, something we will learn to notice and where appropriate tolerate. Another goal will be to provide protection between applications as well as between OS and applications. Because we wish to allow many programs to run at the same time, we want to make sure that the malicious or accidental bad behavior of one does not harm others. We certainly don't want an application be able to harm the OS itself, as that would affect all programs running on the system. Protection is at the heart of one of the main principles underlying an operating system, which is that of isolation. Isolating processes from one another is the key to protection and thus underlie much of what an OS must do. So, what makes things easy to use, such as this virtualization of multiple processes and isolation, is also what makes it secure, which is kind of like a double sword. The operating system must also run non-stop. When it fails, all applications running on the system fail as well. Because of this dependence, operating systems often strive to provide a high degree of reliability. As operating systems grow ever more complex, sometimes containing millions of lines of codes, building a reliable operating system is quite a challenge, and indeed, much of the ongoing research in the field, including some of our own work, focuses on this exact problem. Mobility is increasingly important as OSs are run on smaller and smaller devices. So let's talk about the history of OS. In the beginning, the operating system didn't do too much. Basically, it was just a set of libraries of commonly used function. That's why it's the first term to discuss to describe it. It's just a set of library. For example, instead of having each programmer of the system write low-level I/O handling code, so such as the hardware device or kernel modules, the OS would provide such APIs and thus would make the file system or the life easier for developer. Usually on these old maintenance systems, one program ran at a time as controlled by a human operator. So we cannot do two programs at a time, such as these concurrent programs we have a luxury to use. Now, much of what you think a modern OS would do, deciding what order to run jobs in, was performed by this operator or by the software engineer. It instead of policies deciding which jobs to run first or what programs to currently run, this operator does that. This mode of computing was known as batch processing. So a number of jobs were set up and then run in batch by the operator. So before it was a batch processing because we batch the process to be run by one operator because computers of that point were not used in an interactive manner because of cost. Sometimes could cost hundreds of thousands of dollars per hour. So in moving beyond being a simple library of common use devices services, operating system took on more a central role in managing machines. So notice of it being a set of libraries of commonly used functions. It's already set of different codes for different maybe devices such as I/O, memory, CPU. It's already complex in itself back then, but it is not as intricate today, where it handled this a lots of application at a single time, and where these millions of code came by. So in moving beyond being a simple library of common use services, they took a more central role in managing machines. One important aspect of this was the realization that code run on behalf of the OS was special. It had control of devices and thus should be treated differently than normal application code. Why is this? Well, imagine if you allowed any application to read from anywhere on the disk. The notion of privacy goes out the window as any program can read any file. Thus, implementing a file system to manage your files as a library makes little sense. Instead, something else was needed. Thus, the idea of system call was invented, pioneered by the Atlas computing system. So, because of that, this OS, instead of just a standard library which has an access to the hardware, it becomes a crucial part of the system. And security is the key because back then this system cost a lot of money to produce. So we definitely need some way or to resolve the others of reading this file and then breaking this costly machines. So thus the idea of a system call was invented, pioneered by the Atlas computing system. Instead of providing OS routines as a library, where you just make a procedure call to access them, the idea here was to add a special pair of hardware instructions and hardware state to make the transition into the OS a more formal, controlled process. So instead of just procedure call to access this hardware, the idea was to add a special pair of hardware instructions and hardware state. So you have this state and instruction now to make the transition into the OS a more formal, controlled process. So the key difference between a system call, which again the system call we discussed such as open, write, and close for a file system, and a procedure call is that a system call transfer control jumps into the OS while simultaneously raising the hardware privilege level. So that's what we did in the code when we open. So we transfer the control to a privilege that allows them to access the hardware. User applications run in what is referred to as a user mode by default, which means the hardware restricts what application can do. For example, an application running in user mode can typically initiate an I/O request to the disk, access any physical memory page, or send a packet on the network. But it has an access on memory, of course. Virtual memory because it needs to run, right? But for the CPU, the physical memory page, again, page or the sending the packet, it doesn't have access on that. When a system call is initiated, usually through a special hardware instruction called a trap. So again, this system call used by operating system is initiated through a special hardware instruction called the trap. So this trap, again, we were going to be using that in the further videos, is a special hardware instruction, kind of like kernel modules that used to be abstracted away using a set of library from the first operating system. So the hardware transfer control to a pre-specified trap handler that the OS set up previously. So it transferred that the hardware is actually the one who transfer control to that specified trap handler that the OS did before, and simultaneously raises the privilege level to kernel mode when we are doing this system call. So in kernel mode, the OS has full access to the hardware of the system and thus can do things like initiate an I/O request or make more available to a program. So it can make the network device or the memory or the I/O available. So what it does is that the hardware transfer this control when the system call initiated via trap, and then this control was handled by the trap handler, which was created by the OS before it transfer control. Then it raises the privilege access simultaneously to that program so that it can modify the hardware. So in kernel mode, the OS has full access to the hardware So the program and the OS has the full access to the hardware of the system and thus can do things like initiate an I/O request or make more memory available to a program. So even allocating memory are decides using this trap and trap handle. So when the OS is done servicing the request, it passes control back to the user via a special return from trap instruction. So again, a trap handler which was created by the OS to transfer it to the actual hardware to pass the control simultaneously provide privilege to the OS, which then actually the OS the OS are still the one that used to that passes the control back to the user via a special return from trap instructions, which revert to user mode, while simultaneously passing control back to the user via special return from trap instruction, which revert to user mode, while simultaneously passing control back to where the application left off. So since this program kind of like complex to imagine, but basically it also connected to how the memory of the application put a register in the CPU, kind of like to remember where the application left off. So once it traces privilege, this OS passes control back to the user via passes the control back to user mode via special return from trap instruction, which reverts to user mode while simultaneously passing control back to where the application left off, so that the state of controls where the user left off is handled by OS as well, as you can see. So this is how important OS is. So not surprisingly, one of the major impacts of this drop in cost was an increase in developer activity. More smart people got their hands on computers and thus made computer systems do more interesting and beautiful things. In particular, multi-programming became commonplace due to the desire to make better use of machine resources. Instead of just running one job at a time, the OS would load a number of jobs into memory and switch rapidly between them, thus improving CPU utilization. So instead of batch processing by that one programmer, it allows them to put jobs or processes or multiple programs simultaneously, which allows them to switch back with them if the process is currently being blocked or writing in the disk, because writing in the disk is more time consuming. Thus, it improves the CPU utilization. It is allowed to do other tasks while it's waiting. So this switching was particularly important because I/O devices were slow. Having a program wait on the CPU while its I/O was being served was a waste of CPU time. Instead, why not switch to another job and run it for a while? The desire to support multi-programming and overlap in the presence of I/O and interrupts force innovation in the conceptual development of operating system along a number of directions. I think we'll have to continue with this tomorrow, the desire to programming.